Okay, so today we are going to continue finding equations of tangents and normals, but using your GDC more heavily. You need to do this particularly when you've got unfamiliar functions, but like this, ones we don't know how to differentiate, your GDC will just do it for you. But also be aware you can do it with simpler ones as well. Okay, so today we're going to be substituting into this equation for a straight line because I know you prefer it. Many of you do not like, for reasons unknown, because I like it. But anyway, you don't like the y minus y1 equals m brackets x minus x11, do you? So to recall, in order to get the equation of a straight line generally, you need a gradient and you need a point on that line in order to get the equation of that line. Once you have all those three things, if you do it this way, you can substitute in, rearrange, and then you can get C as well. So we're going to do it that way today, rather than substitute into the other equation. So the first thing we're going to start there, we're going to start by getting M. So the gradient of this particular curve. We're going to do it two ways because it might be nice to visualize what it looks like. So should we do that first? So we want the equation of the tangent to this curve, and then we will, find the derivative. So let's go into graph. Genuinely forgotten what it is already. 4 ln x. So here I go then. 4. I'm going to put times in because sometimes it gets a bit funny, doesn't it? Ln you will find here. So if it's above e to the power of x, so e for ln x, and I'll just close those brackets. And there we go. So it's actually drawn it quite nicely. So there is, that's what this particular function looks like. Now what it's asking us to do in the question is we want the equation of the tangent where x equals 1. So we want the gradient then at that particular point. So let's do that very, very simply on your GDC. If you go into menu, you're going to analyze graph, and here you go to dy over dx. This will give you the gradient at a particular point. We want it when x equals 1. You just type in 1, and then you press enter, and behold, there it is. So it's given us the gradient at that point. So the gradient just at that point, and you can see it is about 4. It's quite steep, isn't it? So the gradient then is 4. I do believe we've actually done this before, so this is just a reminder, really. So the gradient is 4. Isn't that wonderful? Even better news is we know a value of x at that point. The value of x is 1. They gave it to us. How do we find the value of y? Well, you've got to remember, these are pretty similar, these sort of questions. You've got an equation with y in it. So all you have to do is substitute into your equation, your value of x, which is 1, into this equation for y to get the corresponding y value. So it is y equals 4 ln 1. Now, I happen to know that's 0, but I will prove it to you now. So don't really mind where you do this. You go back into your menu and calculate it. So 4 times, and again, you've got to go into control there, ln 1, and then press enter because ln 1 is 0. So I knew that was going to be 0. So we got our two coordinates. How glorious. So y equals 0 and x equals 1. And now we can substitute into this equation. So I know my y value is 0. The gradient at that point, the gradient of the function is 4, times by the value of x at that point, which is 1, plus c. And all I have to do then is rearrange this to get the value of c. So c is minus 4. And then the equation of the tangent then, we know what c is, we know what the gradient is. So when you're rewriting it out, it'll be y equals, well, the gradient was 4, and the y-intercept we just found out is minus 4. So didn't we do well? So that is the equation then of the tangent at that point.